Welcome to the next lecture in elementary statistics at Dallas College, specifically using ALEKS. Today we're going to be looking at chapters and sections 6.4 and 6.5 around the normal approximation to the binomial distribution and how do we assess normality. A binomial random variable represents the number of successes in a series of independent trials. The sample proportion is found by dividing the number of successes by the number of trials. This is just very logical. It sounds a little confusing. But again, imagine flipping a coin. If we're trying to figure out how many times we get heads on the flip, that would be the number of successes, and then the denominator would be how many times we flip the coin. Since the sample proportion is approximately normally distributed, whenever the sample size, n, times the population proportion is greater than or equal to 10, and the sample size times 1 minus the proportion is greater than or equal to 10, the number of successes is also approximately normally distributed under these conditions. That's the bell-shaped curve, remember. Therefore, the normal curve can also be used to compute approximate probabilities for the binomial distribution. Remember, if x is a binomial random variable with n number of trials and a success probability of p, then the mean of x, mu sub x, is equal to n times p, the probability. The variance of x, sigma squared sub x, is equal to np times 1 minus p, and the standard deviation of x, sigma sub x, is equal to the square root of the product of n times p times the quantity of 1 minus p. And in all of these, n is the number of trials, and p is the success probability. Binomial probabilities can be computed exactly using what we've done before. If the number of trials is large, using these methods by hand is extremely difficult because many terms have to be calculated and added together. So if we're doing a large number of trials, like let's say flipping a coin, we may not want to do this 1,000 times and try to figure that out. If the following conditions are met, binomial probabilities can be approximated using a normal distribution. Let x be a binomial random variable with n trials and success probability of p. If np is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10, then x is approximately normal with a mean equal to mu sub x equals np and a standard deviation sigma sub x equals np times 1 minus p. So what this is telling us, if these conditions are met, this product of np and this product of n times the quantity of 1 minus p, both of those being greater than or equal to 10, then we can use a normal distribution, and we can use these formulas for calculating both our standard deviation and our mean of our sample. The binomial distribution is discrete, whereas the normal distribution is continuous. Remember, discrete is like counting numbers 1, 2, 3, and continuous is when you have all those decimals that could be rounded. The continuity correction is an adjustment made when approximating a discrete distribution with a continuous one, which can improve the accuracy of the approximation. A fair coin is tossed 100 times. Let x represent the number of heads that result. Then x has a binomial distribution with n equals 100 and the probability p equals 0.5. Now, how did we get this? This isn't a given. What happens each time we toss a coin? We know that it's equally likely to get heads or tails, so the probability of getting heads is 0.5, half of the times. Okay? If we want to compute the probability x is between 45 and 55, for example, that the probability that the number of heads that result from 100 trials is between 45 and 55. The probability that the number of heads is between 45 and 55, the probability will differ depending upon whether the endpoints 45 and 55 are included. And this has to go with the idea of discrete and continuous. To compute x's between them, notice we're not including those values. The rectangles corresponding to 45 and to 55 should be excluded, as you can see in the diagram to the right. To approximate this normal curve, what we're going to do is we're going to calculate the probability between 45.5 and 54.5, the values you see here. And this way we are excluding the actual values of 45 and 55. If we want to include them, if we want to know the probability greater than or equal to or less than or equal to these values, notice what we do is we can go to a rectangle one less and one greater than the values were here. So now we're going to compute the probability between 44.5 and 55.5, which includes, as you can see from the diagram, both 45 and 55. So this is that continuity correction when we're looking at discrete versus continuous, so to make sure that we have a more accurate computation of the probability, whether we're including those endpoints or we're not including them. So let's look at an example here. You might, if you think you can do this, go ahead and try this. I've left the formulas there. Let x be the number of heads that appear when a fair coin is tossed 100 times. Use the normal curve to find the probability is between 45 and 55 inclusive. The number of trials is 100, so the first thing we want to do is make sure that we can use the normal approximation by plugging n and p, our probability of 0.5, right? We got a 50-50 shot of getting a heads on each trial. So we plug that into our NP and make sure it's greater than or equal to 10, we get 50. We do the same thing times n times the quantity of 1 minus p, and we get the same thing, 50. Since both of these are greater than or equal to 10, we can use the normal approximation and do our calculation here. So our mean value is n times p, or 50. Our standard deviation is the square root of np times 1 minus p, and we get 5 there. From this, we can calculate our z-scores. Because the probability is including, remember we want to go a half a point below, so to 44.5 and to 55.5, okay? These represent our x values in our formula. We just calculated the mean and the standard deviation. So we can see the z-scores are 1.1 and negative 1.1. If we look at table 8.2 for the value at 1.1, we get a probability of 0.8643, right? That's the probability on the right, okay? So that includes everything from 55.5 down to 0. The probability at negative 1.1 is 0.1357. That's everything to the left of this value as well for the probability. Since we want the probability, the area between those two, we take the probability at the larger minus the probability at the smaller, and we get the probability for our problem between 45 and 55, okay? Remember, the areas in the data inside the table when you go to 1.1 represents the area to the left of that point, to the left of, which is also the proportion or the probability for success at that point, and below the probability that that value will be in that range. So we're looking for the area between those 2 points, and that's why we subtract. This isn't the first time we've done this, so hopefully this is more of a refresher than you're feeling it's totally brand new. It's just a different content, but we've done this type of thing with Table A2. Okay. So here this is pretty straightforward. Again, this is a good exercise for you to try. All I'm asking you to do is to match the graph with the problem, right? So hit pause and try these A, B, C, and graphs 1, 2, 3. To approximate the probability that the number of successes is less than or equal to 55, we would find the area to the left of 55.5. I mean, these are pretty straightforward. You can see that the only one with the area to the left of 55.5 is number 2. Greater than 55.5 would be number 3. You can see that area there. And if we did this, we would find the z-score here, right, which would give us the area to the left, and then we would subtract it from 1. To approximate the area x equals 55 exactly, we would find the area between 54.5 and 55.5, as you can see in Table 1. Now again, here we would find those two z-scores. We would find the area for the z-score at 55.5, then find the area at 54.5 and subtract them like we did in the last problem. And so here these are lined up so you can see the answers exactly. So this is just kind of a note sheet. When we're including the areas, the endpoints, when we're including the endpoints, the area is plus and minus 0.5 from the lower value, subtracting 0.5 from the lower value, adding 0.5 to the upper value. If we're just looking for it less than or equal, again, we're including that endpoint, so we're going to add 0.5 to that x value. If we're looking for it to be greater than or equal to a, we're going to, again, subtract 0.5, so we include the point A. And of course here, we would find the area with the table typically, and then subtract it from 1. That happens when we're ever doing the greater than. And if we're doing a specific value for x, we would just subtract, we would find the area between plus and minus 0.5 of that area, or of that x value we're looking for. So let's try another one. The Statistical Abstract of the United States reported that 66% of students who graduated from high school enrolled in college. 100 high school graduates are sampled. Let x be the number who enrolled in college. Okay, we're looking for the probability that less than or equal to 75 students enrolled in college. Well, if we want to use the normal curve, we first have to test that it's possible. So again, our n is, how many are we doing? 100 high school students, so n equals 100. And our success probability is given in the problem too. 66% of students who graduate high school enroll in college, so that's our P. Now we can do both our calculations. NP, we get 66, that checks out. N times 1 minus P gives us 34, that checks out. We can use the normal approximation. At this point, I want you to really hit pause and see if you can do this problem. It's very similar to what we just did before. This one's even a little simpler since we're only looking for the values less than or equal to 75. So again, I've left all the formulas up here to help you go through this problem. Find the mean, find the standard deviation, and then find the z-score so that you can look in the table to find the probability. Here's our mean, here's our standard deviation using the formulas, here's our z-score. Now why didn't we use 75.5 here? Well, you cannot have a, because we're talking about people, you can't have a continuous person. You can't have a 1.5, you can't have a decimal person. So in this case, we didn't have to do the 75.5, okay? When we look in table A2, we get 0.9713. So we have a 97% probability that the number of students who enroll in college will be less than 75. This is a little practice for you as well. So what I'm asking you to do here is check and see if we can use the normal approximation, and if you can, calculate the indicated probability. I'm not going to walk through these. I'm going to show you the answers, but I think this would be a great exercise to do what you did in the last two problems and to try it on your own. The more you get active while you're watching these videos, doing the exercises, the more mastery of the material you're going to have instead of just passively watching it. So hit pause and see if you can do these four problems. First, check to see whether you can use the normal curve, and if you can, then calculate the probability just like we did before, finding the mean, finding the standard deviation, and then calculating the z-score to find the probability. Okay. So notice when in this first one, we cannot use the normal curve because the first value is less than 10. And remember, it has to be greater than or equal to 10. In the second case, it's also the situation. The second calculation, n times 1 minus p, is also less than 10. In the third case, we can, if we multiply np, we get a value greater than or equal to 10, and n times 1 minus p is the same case. And then if we go through the calculations, we get a probability of roughly about 7%. Okay? I really recommend that you do this and see if you can get that answer. And in the last case, it's the same case. When we do the test to see if we can use a normal curve, we pass, and the probability is roughly 12.5% or 0.125. So we're halfway through our lecture. We just covered the continuity correction and how to use the normal curve to approximate binomial probabilities. This is a good time to hit pause and for you to do a mental pause. Maybe get up, go grab a snack or a drink, take a walk, even if you just stretch for a couple minutes, walk around your house, maybe even ponder life. I have a great book called Ever Wonder, and it just has these random questions, and this is one question from there. What do you pack to pursue a dream, and what do you leave behind? So again, take a little break and then come back and continue. So here what we're going to do is use graphs in 6.5 to kind of assess normality, and you can see that we're using pretty much every graph that we've looked at before: dot plots, box plots, histograms, stem and leaf, and then I don't think we've done quantile plots yet, and so we'll see that today. Many statistical procedures require that we draw a sample from a population whose distribution is approximately normal. Often we don't know whether the population is approximately normal when we draw the sample. Now remember, approximately normal is that bell-shaped curve. We can easily find out if our sample is that, but we don't always know if the population is that. So the only way we have to assess whether the population is approximately normal is by examining the sample. And there are three important ideas to remember when assessing normality. We are never looking for exactly normal, okay? We're looking for roughly normal, okay? If the data is, relatively a bell curve, that normal curve, then we can make some great inferences from it and some conclusions about the population. Assessing normality is more important for small samples than for large samples. Large samples tend to follow what you would expect, the proportions from the population. The larger the sample, the more likely we're going to get close to population averages. And there's no hard and fast rule, so it's not easy to always determine what's happening So we're going to follow some process kind of questions. So it's easier to figure out when to reject normality than to say, okay, this is always the case. So we will reject the assumption that a population is approximately normal if the sample has any of the following features. First, the sample contains an outlier. The sample exhibits a large degree of skewness. Remember, skewness is when it has a tail to the left or the right. So the data ramps up from the left or it trails off to the right. And the sample has more than one distinct mode. Remember, a mode is like the top of a hill. In our normal curve, we have this bell-shaped curve, so there's only one hill. So what this is talking about is if there would be multiple hills, multiple modes. If the sample has none of these, we will treat the population as being approximately normal. So let's look at a data thing here, an exercise. The accuracy of an oven thermostat is being tested. The oven is set to 360 degrees and the temperature when the thermostat turns off is recorded. A sample of size 7 yields the following results. Is it reasonable to treat this as a sample from approximately normal? When we just look at the numbers, it's really hard to figure that out. But what we're looking for is outliers, whether it's skewed and whether it's more than one mode. One of the things we can do is just put the information, the data, in that numerical order. But even more so is if we look at the lowest point and the highest point, and we create a scale like we've done here, we know that all the data is between 350 and 370, and then we make equal units between those two marks, and then plot each of the points. Okay, 355 is here, 352, etc. Then we can kind of see the distribution of the data. This is just a simple dot plot. The data looks pretty evenly distributed. There's no outliers. There's no skewedness, like a large number of data points here at this end or at either end. And there's no indication that there's more than one mode. Okay? So we could assume that the population is approximately normal. Here's another case. At a recent health fair, several hundred people had their pulse rates measured. A simple random sample of 6 records was drawn, and the pulse rates in beats per minute were as follows. Is it reasonable to treat this as a sample from an approximately normal population? I don't know if you're getting to see this cat move, but he's pretty funny when he's doing it. When I teach this in class, he never shows up, so I'm not sure why that is. So again, we do a dot plot between 65 and 100 because all the values are there. And the first thing hopefully you notice right away is that there's this value that's separated from a long distance from the other. Most of the values are between 65 and 80, and yet this one is closer to 100. So immediately we see the first point, we have an outlier. As soon as we see that, if we have any of these situations, then we reject the assumption that the population is normal. Here we're looking at an insurance adjuster has a sample of 20 estimates in hundreds of dollars for repairs to cars damaged in collisions. So for example, this is $1,200, $210? Yeah, these are in hundreds of dollars. This is $1,570, etc. So these are just accidents and estimates for the repairs to the cars, okay? What we've done here is created a box plot. Remember, a box plot shows the quartiles left and right. The line in the middle is the average value, and then the whiskers go to the extreme values to the left and to the right of the quartiles. Okay? So the first thing we're looking, are there any outliers? Well, outliers are marked by stars, and outliers are anything that's beyond the whiskers of the box plot. Okay, so we don't have any outliers. Now skewedness, it looks like it's slightly skewed to the left, but you can notice this whisker is a little bit longer than the one to the right. Also, the mean is not in the exact middle. So there's a bit more data here. Now, you might say, okay, well, this is skewed, so we wouldn't count it. But remember, we're not looking for perfection. We're looking for roughly normal. And so while this area is a little bit larger to the left than to the right in the rectangle and the whiskers are larger, it's not extreme. So I wouldn't say it's skewed and there's no indication of one mode. Okay. So in this case, we could assume or treat the sample as approximately normal. Here we have another box plot. This time, this is the amount of recycled newspaper in cubic feet collected each week. Again, now we have another box plot, and the first thing we can see is we have an outlier. So that would automatically rule out the sample being treated as approximately normal. In addition, look at the difference in the whiskers. The whisker to the right is really large. Inside the box, the right area is a little bit larger, but the whisker really shows off that there's a lot of skewedness to the right. So although we didn't even have to check the skewedness because we can see there's an outlier, both of those do kind of play in here. Here we're looking at a simple random sample of 20 pitches from a high school baseball game. And these are the speeds of pitches in miles per hour. So now we're using the histogram. Now again, you might think, oh, this is multimodal or more than one mode because we have no data here and here. But again, we're not looking for perfection. Having, I don't know how many are here, several data points here does not necessarily mean that this is not normally stretched. To me, this is roughly normal, even though there's this little spike here. It's not so far away. I mean, we're talking about what, 2 or 3, only one gap in there, 1 mile per hour that wasn't measured. So it's still grouped roughly together. Notice it's lower than the middle point. So I feel like there aren't any outliers. There doesn't seem a big degree of skewedness, and this is really not evidence of a mode. So we could assume that the sample is approximately normal. The sample is from an approximately normal population. This one's quite obvious here. You can see immediately this is a shoe manufacturing testing a new type of sole. You can immediately see the data is really skewed to the right. So there's not much reason to go any further. So we would not treat this sample from an approximately normal population. Stem and leaf, remember typically the stem is the first number and then the leaves are all the second, third, or fourth numbers, and we create some kind of diagram from that. When we look at that, here instead of doing 3 as just the stem, what they've done is they've included the first number as this stem twice. So the first one would be, I would guess, 0 through 4. And the second grouping of 3 would be 5 through 9. So it kind of gives you a better, it's detailing, there's not much data here, so it's allowing you to kind of see, and you can really see when they've broken it down this way, how it does really mirror a normal curve with our mode being at the lower root 5 level. So when they broke down the stems, this gave us more detailed visual image. And again, we could treat this sample as if from a approximately normal population. So again, you can hit pause here, try these. Just give a thumbs up or thumbs down whether you think these are from, you can treat the sample from an approximately normal population. So hit pause. Just 4 quick answers. You can see the outlier, looks relatively normal, and here the data is skewed to the right. You see most of the data is in the front. Normal quantile plots are somewhat more complex than dot plots, histograms, and stem and leaf plots. This shows how we construct a. It is a little confusing. A simple random sample of n equals 5 is drawn, and we want to determine whether the population came from is approximately normal. The 5 sample values in increasing order, you can see those x values. X values are always the sample data we collect, are there. There are 5 of those data points that we number 1 through 5. Since we want to spread these values out evenly, we then create sort of an assigned value by multiplying 1 over 2n to the first sample, 3 over 2n to the second, and so forth. The last sample will be 2n minus 1 over 2n. And really this formula works for anyone. For the first sample, we'd have 2 minus 1 over 10. 2 minus 1 is 1 over 10, or 0.1. If the second value, the second sample, what we've done is actually just evenly divided these. Since there's 5 points, you'll notice that they're all 0.2 apart. Okay? What it does, it allows us to find the z-scores corresponding to each of these areas, specifically the a sub I value. And then if we plot the points, the actual data point with the z-score that's connected to that area that we calculated, and if they are roughly in a straight line, then we can treat the population as approximately normal. You can see here that they are all pretty close to that straight line, so we can treat this population normal. I have not used quantile plots very often, and actually I don't think I've ever used them in a professional setting, but if I did, it would always be done with a mapping software like you see here. Remember that at the back of your text there are technology step-by-steps, which you're seeing part of that here, and then there are also examples, and they show you exactly how to calculate that, whether you're using Excel or you're. Again, we've gone through all the topics here. These are the things you should know. You might want to hit pause and make sure you feel comfortable looking at these. I think that most of these were pretty straightforward, except for the last one, the quantile plot, so you might want to spend a little more time there.